All right, so we're going to start with naming compounds here, and hopefully some of this is going to be a review for you because you probably named simple ionic compounds and simple molecular compounds last year in grade 9 science. Okay, so some of this will be a review, but we're also going to try some stuff that's a little bit more complex, some special rules that come up involving certain types of compounds and things like that. All right, so the key points for today, the things we got to be able to do, okay, identify a compound as being ionic or molecular. Right? Does anyone remember how we can tell them apart? Okay, if it's got prefixes in the name, it's definitely a molecular compound. Okay, what are molecular compounds made out of? What do they have in them? Other way around. Yeah. Okay. So an ionic compound is a metal and a nonmetal. Okay. And a molecular compound is two nonmetals. So we should be able to just look at a compound and know right away whether it's ionic or molecular. Okay. From our periodic table. If we've got something from the left-hand side in that compound, it's ionic because stuff on the left is a metal. All right. So if it has a metal and it'll be the first thing in the compound, it's ionic. If the first thing in the compound is a nonmetal, it's molecular. Okay. Is that pretty simple? Right. That's all we have to remember there in terms of being able to tell them apart. Okay. Then we have to apply the right naming rules and all that kind of stuff. Okay. Second thing, we got to be able to write formulae and proper names for chemical compounds. Okay. So ionic compounds, like we just said, are made of a nonmetal and a metal. Okay. So they got one from each side. We always name the metal first. Okay. And the nonmetal second, just because that's the way the periodic table goes. Okay. Now, the thing about ionic compounds, okay? Ionic compounds and molecular compounds are different, not just because one has a metal in it and the other doesn't, okay? But they're different in the way the electrons move when the compound is formed. Okay? We know from yesterday that the electrons are in this cloud that surrounds the nucleus. Okay? Because they're not in the nucleus, they can be lost. Okay? Atoms can lose electrons. They can also be gained. Certain types of elements will gain electrons, right? But because of the nature of electrons and how fast they move and how far some of them are from the nucleus, they can come off. Okay? In an ionic compound, these electrons essentially get traded. Okay? Metals typically give up electrons, where nonmetals typically accept them. All right? So there's this kind of trading that goes on when an ionic compound forms. All right, so a nonmetal will pick up an electron and a metal will lose it. Okay, now, can a metal lose more than one? Yes, there are some metals that will lose 2, 3, 4. Okay, it depends on the metal. All right, so that's what we're going to look at here. Okay, so in an ionic compound, obviously, the big thing we need to remember here, it's got a metal and a nonmetal, okay, in it. Okay, they react to form a new molecule. Okay, in these molecules, electrons are typically lost by the metal and gained by the nonmetal. Okay? Now, all elements want to have what we call an outer shell that's full, or a valence shell that's full. Now, to explain what that means, we got to look at Bohr's model of the atom. Okay? Because there are still some things we accept about the layout of Bohr's model. Not necessarily that that's what an atom looks like, but when we're dealing with electrons moving, it's much easier to say the electron is here and use Bohr's model than it is to say the electron's somewhere. And now it's going to do this. Okay, so Bohr's model is handy kind of in that way. So if I'm looking at, let's say, sodium, for example, okay, we know that in the nucleus of a sodium atom, okay, there are 11 protons, okay, and there are 12 neutrons. Okay, so we've got, and then how many electrons will there be? If there's 11 protons, there has to be 11 electrons. Okay, at least to start with. Now, according to Bohr, there were energy levels, and Bohr was kind of right about the energy level thing. It just doesn't look like planets orbiting the sun. Okay, in the first energy level, okay, we have 2 electrons. Okay, in the level outside of that, there are going to be 8. Okay, now we're up to 10. We need one more, so there's one more shell. And in that outer shell, there's only one electron. Now, if you're a metal or a nonmetal, you want to have your outer shell full of electrons. It just makes you more stable. You're happier that way for whatever reason. Okay? that outer shell that only has 1 electron in it can hold 8. So which is easier? Lose 1 and have a full outer shell, or pick up 7 to get an outer shell that's full? Lose 1. Yeah, it's way easier for sodium to lose 1 electron and go with the other shell being full. Okay, so that's why sodium always loses 1 electron. Okay, that's the easiest way for it to achieve a full outer shell. Okay, if we're looking at chlorine, okay, if we're looking at like sodium chloride, a compound going together here. Okay, chlorine is going to have, what do we got here? 17 protons. It's going to have 18 neutrons, okay, something like that. So we got 17 protons, we got 18 neutrons, and we got 17 electrons. So we got the first shell, it's got 2 in it. Okay, we got the next shell, 1, 2, right? Now we're up to 10, and then the next shell can hold 8. But there's only 7 in it. So, is it pretty obvious now why these two get along so well? Yeah, they each have what the other needs. Okay, chlorine can accept an electron, and sodium needs to get rid of one. All right, that's why sodium chloride is such a common compound. Okay, it's table salt. So what happens here is this electron essentially gets traded to chlorine. The two atoms stay bonded together, but it's a weak bond. Okay, ionic bonds are very, very weak because really, this sounds awful from a sociological perspective, but they each got what they wanted. Okay, what reason is there for them to stay together? I know that sounds awful. Don't put it in a sociological context. This is chemistry. Okay, but really, they both have a full outer shell. So if they separated, they would both still technically be happy. Okay, so that's what happens lots of times with ionic compounds. Is the bond breaks very easily. That's why ionic compounds are also very soluble in water. Okay, if you put salt in water, does it dissolve? Can you dissolve quite a bit of salt in water? You can. It's highly soluble. Okay, but when the salt enters the water and starts to dissolve, the sodium and chlorine separate. Okay, and so now you have a positively charged particle floating around, and you have a negatively charged particle floating around. In the solution. Okay, which one is positively charged, sodium or chlorine? Okay, sodium has lost 1 electron, and chlorine has gained 1 electron. If it has 1 extra electron, so it's going to be negative, right? Okay, so chlorine has gained an extra electron. It now has 18 electrons and 17 protons. So it's got 1 more negative charge than it has positive. Okay, so it's negatively charged. Meanwhile, sodium has lost an electron. It now has 11 protons and 10 electrons. So it's positively charged. Okay, now as a result, the solution you've made by dissolving salt in water will conduct electricity. Okay, because there's positive and negative ions in there that can allow the electrons to pass. Everyone with me? Because pure distilled water actually doesn't conduct electricity. Okay, tap water does because it's got ions in it. Okay, positively charged and negatively charged particles. But distilled water won't. Okay, so basically what you need to know is the stuff we've underlined here. Okay, we've got these full outer shells. Okay, we got electrons lost by metals, gained by nonmetals. Okay, that's what happens in an ionic compound. All right, so binary compounds. Okay, binary means they have 2 parts. Okay, if we're naming a binary ionic compound, we always name the metal first. All right, metal first, and then the name of the nonmetal. Okay, the name of the metal is stated in full with no changes. Okay, we do not alter the name of the metal at all. However, the name of the nonmetal is changed to an "ide" ending. All right, so if I have NaCl, I don't call this sodium chlorine. I call it sodium chloride. Okay, and this stuff here would be magnesium iodide. All right, everyone follow me there? So all we do is change the nonmetal's ending, sorry, to "ide," right, which is pretty easy. All right, so other examples here, magnesium oxide, okay, not magnesium oxygen, right? Magnesium oxide just sounds better, okay, when they all have kind of the same ending. Okay, questions on that part? That's probably a review, right? We all knew that before. Okay. All right, so we have to name both ions, but here's something people don't realize, and I don't know if it's just because it never gets taught or it's just such a bad habit from English class. Yes, I said that. English teaches you bad habits because you want to capitalize names. Well, in English you should. In fact, anytime you should. The thing is, the name of an ionic compound or a molecular compound is not a proper name like John Smith would be. Okay? It's a designation, which does not require capitals. Okay? So the names of chemical compounds are never capitalized. All right. So, okay, so when we're using the formulas, okay, we'll talk about balancing the charges here in just a minute. Okay, a true compound should have a net charge of 0. Right? When we looked at sodium and chlorine, one of them was positive, one of them was negative. Did it end up being 0? That whole compound? Okay. Sodium gave up an electron and had a charge of positive 1. Chlorine gained an electron and had a charge of negative 1. Did those cancel each other out? Yes. Okay. So that's what always has to happen in an ionic compound is your charges have to add up to 0. That's why you do the drop and swap. You guys remember that from Science 9? Okay. The drop and swap makes sure that that always happens without you having to do any math. Okay. So it's a nice little trick. Okay. So when we're looking at this reaction here, okay, we're producing an ionic compound. Okay, aluminum chloride in this case. So we have aluminum reacting with chlorine to produce AlCl3, which is aluminum chloride. Do I need to tell people that there are 3 chlorines? People will look at that and going, it seems kind of important, but I'm not really sure. The answer is no. I don't have to tell them. Right? Because when aluminum and chlorine go together in a compound, they can only go together that way. Right? That is the only possible combination for aluminum and chlorine to go together in. Okay? Why is that? Well, because aluminum, if you look on your periodic table, aluminum has a charge of 3+. Okay, everyone take out their periodic table. We're going to be referring back to it a whole bunch today. Okay, so if you look on your periodic table for aluminum here, it's number 13. Okay, and underneath the atomic mass, okay, which is 26.98, you see a 3+. Okay, that is aluminum's ionic charge. Anytime aluminum is in a compound, that will be its charge, 3+. That means it loses how many electrons? 3. Okay, leaving 3 extra protons hanging around with no one to love them, I guess. All right, so we have a charge of 3+, and that is going to be combining with chlorine, which has a charge, according to your periodic table, of -1. Okay? This compound has to have a charge of 0 when all is said and done. So how many chlorines do there have to be in order to make that happen? 3. Okay? That's where you do the swap and drop, right? You take this, you swap it and drop it, so the 3 goes here. Okay? We don't write 1s, and we got AlCl3. Right? That's why we don't need to put prefixes on ionic compounds. There's only one way that they can go together. Yes, copper is what we call a multivalent metal. There's a whole bunch of them on there, and I'll get to that if you give me about 10 more minutes. Okay? Yeah, there's some special rules that go along with those. Okay? And yes, there are some that have more than one possible charge. Okay, everyone good with that? All right, so for the naming, metal first, non-metal second, enzinide. Okay, for the formulas, we write the charges and drop and swap. Okay, I lied, it wasn't 10 minutes, it's like right now. Okay, so multivalent metals. Okay, metals that have more than one possible charge. Okay, here's our issue. I just said you never need to tell people how many of anything there is because there's only one way that these two things can go together. That's still true. Okay? However, there are some metals that for some reason sometimes give up 2 electrons and sometimes give up 3. Okay? It all depends on which one you got. So what we have to be able to do is tell people which one of those we were using. Because if we don't, this compound and this compound, which are obviously different, would have the same name. Okay? They would both be iron oxide. Well, we can't have 2 chemicals that are different have the same name. Okay? That could end up killing people. Like, let's say, for example, I'm talking about some experiment that I did where I was testing, let's say, the effect of iron oxide, I don't know, on, let's say, hair growth. I don't know. It doesn't have anything to do with that, but let's just say it does. Okay? And I keep telling people about how if they rub iron oxide on their head, okay, their hair will grow faster, or they'll grow more hair. I'd probably get rich with something like that if it actually worked. Okay? Let's say I'm doing that, and I keep talking about this iron oxide, and I mean this stuff, which is rust. Perfectly harmless, really. Okay? But instead, someone grabs this stuff, which is not rust and is poisonous. Okay? And they rub it on their head and they die. Well, I'm kind of at fault then because I told them to. Right? I didn't say clearly which iron oxide I was talking about. Everyone follow? Okay? So it's pretty important to have some way to tell them apart. Now, difference here is that iron, if you look on your periodic table, can have a 2+ charge or a 3+ charge. Okay? We have to be able to figure out which one it is. Okay, so let's say I've got this iron, and I've got this iron oxide over here. Okay, if iron can have more than one possible charge, I need to be able to figure out which iron I'm working with. Does oxygen have more than one possible charge? No, it's always -2. Okay, so I can use oxygen to figure out what the charge on iron was. Okay, so in this compound here, I have one oxygen, and its charge is always -2. I have how many iron here? 1, right? If there's no numbers, there's 1. Okay, so there's 1 iron here. If I want this compound to be neutral, iron has to have a charge of +2. Okay, so now looking at that, I now know that that stuff is iron, little Roman numeral 2, oxide. Okay, and that's how I tell people the difference between iron 2 oxide and iron 3 oxide. All right, is I put in the little Roman numeral. Okay, the only thing I have to do to figure it out is use my non-metal. Okay, to figure out what the charge here would be. Now, on one like that, it's pretty easy because they're the same. Okay, on one like this, it's still fairly easy. Charge on oxygen is always -2. How many oxygens are there? 3. So how many negative charges are in this compound? 6. Okay, because every oxygen has 2. So there's 6 negatives. I need to have how many positives? 6. All right, so if I have to have +6 and I only have 2 irons to do that with, the charge on iron must be +3. Okay, is that very hard math? Okay, not too tough, right? So this is the iron with the 3+ charge. So this stuff is iron, Roman numeral 3, oxide. All right? So you just have to do a little bit of math. Now, 1 or 2 people often notice this and they go, Coder, I could just reverse the swap and drop. I could just go over here, and that would tell me the right answer. Well, it does about 2/3 of the time. Okay? It doesn't work, however, on one like this. If I reverse the swap and drop, what is that telling me the charge on magnesium is? How many oxygens are there? 1. Is the charge on magnesium 1? No, charge on magnesium is 2. See, it doesn't work. Okay? It works about 2/3 of the time. I'm just not a gambling type. Okay? I like to get it right every time. All right? So what you do is you use the non-metals charge and how many of it there are to figure out what the charge on the metal would be. Okay? And you only have to do that if you're using a metal that has more than one number in its box. Okay? So that's going to be basically iron, copper, nickel. Those would be the most common ones. Lead would come up occasionally. Okay, most of the other ones that have more than one possible charge, we don't deal with very often. Okay, so most of the time you're going to be dealing with iron, lead, nickel, copper. Okay, as your multivalent metals. There are others, obviously. Okay, but most of the time those would be the ones we'd be dealing with. All right, everybody okay with that? We'll go through a couple others here. Let's try this one. Okay. Copper has more than one possible charge. It can be a 1 or a 2. Okay, I want to name this compound properly. Okay, I know it's copper something oxide, right? Because I named the metal first and the nonmetal second. But I need to figure out which copper it is. So I use the nonmetal. Okay, the nonmetal has always got the same charge. So in this case, because I used oxygen again, okay, oxygen is -2. So if I want this compound to have a charge of 0, I need to have 2 positive charges. And I have 2 copper to get them from. So what's the charge on each copper? 1. Okay, all right, you guys try this one. Okay, that's manganese, not to be confused with magnesium. Okay, so that you can find it quickly, it's number 25. Okay, and bromine is number 35. That is a 4, yes. Anybody got it figured out? Okay. It's the Roman numeral for 4. Okay, this is manganese 4 bromide. Okay, the way I do that, bromide always has a charge of -1, which means I have 4 negative charges. I have to have 4 positive charges, and there's only 1 manganese to do it with. So its charge has to be +4. Okay, and you can see on there that one of the possible charges for manganese is 4. All right. Okay, so this is manganese, and then IV, okay, is your Roman numeral for 4. In case you've forgotten your Roman numerals, 1, 2, 3, 4, 5, 6, 7. I can't think we'd go much further than that. Okay, I think technetium is the only one that has a charge of 7, so okay, you won't need to know your Roman numerals any higher than that. Okay. V's stand for 5, and the way Roman numerals go is if it's on the left, it's 1 less than that, or 2 less than that. Okay, if it's, okay, that's just V. If it's on the right, it's 5 plus 1, which is 6, 5 plus 2, which is 7, right? Everyone with me there? This is why the Roman Empire fell. Okay. All right, I want you guys to try these. There are no multivalent metals on there, so none of these are going to need Roman numerals, okay? I just want you to name these ionic compounds. Now, let's say do the first 5, okay? So go to number 5 and stop there. Don't go any further than that, okay? Do the first 5, and then we'll go over them together, okay? And just kind of review the rules here. So, quick review of the rules. Metal gets named first, non-metal gets named second, and ends in "ide." Okay. I'll give you a couple minutes to try that. So obviously we've done number 1 already. Okay, if we're naming that metal first, non-metal second, we're looking at sodium chloride. No capitals. Okay, got to break that habit right now, guys. Okay, number 2, what's K stand for? Potassium, and F is fluorine. All right, so we got potassium. That doesn't have 2 T's in it. Doofus. Okay, fluorine can be spelled many ways. I choose to spell it the way that has less letters. Okay, I think on your periodic table it has a U in it. Okay, but there's more than one way to spell it. Okay, so we're looking at potassium fluoride for number 2. All right, number 3, we got hydrogen and iodine, so this is going to be hydrogen iodide. All right, number 4, I've got calcium and bromine. So what is this stuff going to be called? Calcium bromide. Okay, and again, the big thing to remember here is that we do not have to put in any prefixes for an ionic compound because there's only one way for calcium and bromine to go together. All right, and then number 5, I've got aluminum and I've got astatine together. So this is going to be aluminum astatine, right? All right, let's try 6 to 10. Okay, give you a couple more minutes to try 6 to 10 there. So for number 6, I've got cesium and I've got sulfur. So this is going to be cesium sulfide. Okay. For number 7, I've got sodium and oxygen. So this is going to be sodium oxide. Okay. For number 8, barium and selenium. Now, this one here, you can have a couple of different ones. You can wave at your friend later. Okay. Now, I can have this and be barium selenide. Okay. Or some people write it selenamide. Either one's right. Doesn't really matter. Okay. It's like, you know, if you go to Britain, they pronounce aluminum aluminium. Actually, you're supposed to pronounce it that way, but we in North America are stubborn. Okay. I'm not going to drink out of an aluminium can. I'm just not. Okay. Okay. All right. Number 9. Okay, we've got radium and we've got tellurium here. So we got radium telluride. Okay, and for number 10, I've got lithium and fluorine, so that's lithium fluoride. Okay, how are we doing on those? Getting them right? Okay, let's do the last 4 here real quick, and then we'll move on to a couple of other little tricks that you probably didn't learn last year. All right, so let's check these last 4 here. Okay, so on number 11, I've got rubidium and I've got sulfur, right? So we've got rubidium sulfide. Okay, here I've got strontium and iodine, so that's strontium iodide. Okay, for 13, calcium and oxygen is calcium oxide. Okay, and for 14, we got magnesium selenide. Whoa, that's capital. Can't do that. Selenide. Okay. If you look at the top of your periodic table, okay, you'll see the table of polyatomic ions up there. I thought I had the periodic table in here. Hang on. So on the top of your periodic table, you've got this. It says table of common polyatomic ions on it. Okay? Now, in there, you will find things that look like they should be compounds because they're more than one element. Okay? But they're not. They're not compounds because all of them have a charge. Okay? And we've already said that a true compound has a charge of 0. Okay? These are essentially groups of atoms that go together and bond, but still somehow retain some sort of charge. Most of them are negative. Okay, I think only ammonium is on there that's positive. It's the second one from the top on the left. Okay, the rest are all negative. Okay, and we can see that they all have kind of strange names. Okay, sometimes you're going to get a compound that has one of these in it. It really isn't all that much more difficult to name or write the formula for. Okay. You still apply all the same rules you would to a normal ionic compound. It's just now you've got this group of atoms to put in instead. All right, so we'll quickly look at how that's going to work here with a couple of examples. Okay, let's say I've got this. Okay, I've got lithium, and then I've got two other elements along with it. Anytime you have a compound that has 3 or more elements in it, you're going to be looking at your table of polyatomic ions. All right, because it's going to start with a metal, okay, and you're going to have to look for the polyatomic ion that is attached. Okay, now you can find in there OH somewhere in the middle, I believe, of your chart there. Okay, middle row, fourth from the top. Okay, what's the name of this stuff? OH is hydroxide. Okay, if you look on your table of polyatomic ions there, okay, fourth from the top in the middle row, this stuff is hydroxide. So this whole compound then would be lithium hydroxide. Okay, already ends in "ide", so I don't have to make it end in "ide". Okay, the only thing that's different about naming these is you do not change their name at all. All right, so if I've got, let's say, one that doesn't end in "ide", let's say, that, CaSO4. Okay, SO4 on your table of polyatomic ions is sulfate. Okay, well, if I change that to "ide", it says sulfide. Well, that's this. Is that the same thing? That's why we have to leave all the polyatomic ions with their name the way they're written. So this stuff is calcium sulfate. Okay, is the naming pretty straightforward? I mean, really, you're just writing what's on your periodic table. And you're always going to have this, by the way. Okay, you'll have this on quizzes, your unit exam, your final exam, all of that. Okay, you're never going to have to memorize the stuff that's on here. All right. What if I'm given the name, okay, and I need to make the formula? So let's try. Let's say I need to make the formula for that. Magnesium hydroxide. So what's the symbol for magnesium? Mg. Okay, and magnesium has a charge of 2. All right, so we write that down just like we would for a swap and drop for anything else. Hydroxide is OH. Okay, and its charge, according to your table of polyatomic ions, is -1. Right. Okay, so when I swap and drop, this is going to be how many Mg's am I going to have? 1. How many OH's am I going to have? 2. Now, make sure you write it that way. I'm going to have 2 OH's. Does that say I have 2 OH's? No. That says I have 1 O and 2 H's, which is not the same thing. This is one of those weird rules that goes along with these. If I want to say I have 2 OH's, how would you do that in math? Yeah, exactly. You'd use brackets to say multiply everything by 2. Right? So you use brackets in chemistry. All right? So anytime you got a polyatomic ion, when you swap and drop and need more than one, put brackets around it. Okay? Now, that's the same thing here for sulfate. Okay? So calcium sulfate's SO4, but what if it was, let's say, calcium nitrate, because that one will need it. Okay, if I'm looking at calcium nitrate, I'm going to have Ca, which is 2+, and nitrate, which is NO3, and has a -1 charge. So when I swap and drop, okay, where do I put the brackets? Do I put the 3 inside or outside? Outside. Well, actually, sorry, no, I put the brackets outside of the 3. The 3 stays inside the brackets. Okay, and I put the 2 there. I need 2 nitrates. Nitrate is NO3. Okay, I don't change ever any of the numbers that are in a polyatomic ion when I'm writing it out. Okay, those polyatomic ions are written that way, and they stay that way. All right. So just a couple of new rules you probably didn't learn last year in Science 9, but really they're just the same application of the other rules, just with a couple of little exceptions for them. All right. So now I want you to try these ones. These ones have multivalent metals in them. So they're going to need what? What do you have to put in the name? Roman numerals, right? Okay, so these ones are going to need Roman numerals. Okay, so give you let's say do the first 4 here. Okay, do the first. Actually, we'll do the first one together because we've done it already once, just to remind you how this works. Okay, this stuff is going to be iron oxide, but because iron has more than one charge, I've got to figure out which charge it is. To do that, I use the nonmetal because nonmetals always only have one charge. Okay, oxygen's charge is always -2. So there's how many negative charges here? Right, there's 6 negatives. That means I need 6 positives to make this compound work. If I only have 2 iron to do that with, each iron is +3. So this is iron 1, 2, 3 oxide. Okay? So you do 2, 3, and 4. I'll give you a couple minutes, then we'll go over those together. All right, let's have a look at number 2 here. CO stands for cobalt. Okay, so we got cobalt here. And we got sulfur. So this is going to be cobalt something sulfide. Sulfide's charge is always -2, so cobalt's charge must be +2. All right, so this is cobalt 2 sulfide. All right, number 3, we did one like this just a few minutes ago. We did manganese bromide. Okay, now it's manganese chloride. Okay, that's no big deal. All right, chlorine is always -1. So that gives us 4 negative charges in total. There's only one manganese, its charge has to be +4. Right, so this is manganese 4 chloride. Okay, and for number 4, copper can have a charge of 1 or 2. Okay, in this case, it's probably going to be 2 because sulfur is always -2. Agreed? So this is going to be copper 2 sulfide. All right, try the last 6 there. Give you a few minutes to finish those up, and we'll go through them together. If you're having trouble, let me know. I can come give you a hand. All right, let's have a look at a few of these. All right, so for number 5, SN is tin. Yeah, okay, it's one of those tricky ones that actually is from their Latin name. Okay, so we got tin and we've got telluride. Now, bit tricky here. Okay, tellurium is always a -2 charge, which means I have 4 negatives to get rid of. If there's only one tin, tin has to have a +4 charge. Okay, and that is one of its possible charges. Tin 4 telluride. All right, for number 6, I've got Hg, which is mercury. Okay, and it is with astatine, so that's mercury astatide. Okay, astatine is always a -1 charge, so this has to be mercury with the 2+ charge. Okay, because there's 2 astatines, that gives me 2 negatives. That's got to be +2. All right, for number 7, I've got polonium with iodine. Okay, iodine's always a -1, so that means that I have 4 negatives. So polonium has to have a charge of +4. So it's polonium 4 iodide. Okay, for number 8, I've got antimony with sulfur. Okay, so okay, sulfide's charge is always -2, which gives me 6 negatives that I have to balance out. So I got to have 6 positives over here. 6 divided by 2 is 3. All right, so this is antimony 3 sulfide. It's probably not a real compound. I'm just throwing things together here. Okay. For number 9, I've got nickel with nitrogen. So we're going to have nickel something nitride. Okay, nitride is always -3, so that gives me a total of, again, 6 negatives. I need 6 positives over here, so every nickel has a charge of 2. Okay, and lastly, we've got ruthenium with oxygen. Okay, so we got ruthenium oxide. Every oxygen's minus 2. Okay, so negative 2 times 2 is negative 4, which means my one ruthenium has to have a charge of 4. All right, is that making sense to everybody? Okay, it's a little bit of practice. I think everyone will get that pretty good. All right, so yeah, we'll start on molecular compounds today. Okay, quick review what a molecular compound is. Okay, molecular compounds happen when you have two nonmetals joined together. Okay, big thing that's different between a molecular compound and an ionic compound is what happens with the electrons. Okay, in an ionic compound, we said the electrons simply get traded. The metal loses them, the nonmetal gains them. Everybody's happy with their full outer shell. Okay, but now you've got nonmetals bonding with each other, and nonmetals want electrons. So there isn't going to be a nonmetal that's going to be giving up electrons. It's going to want to hold on to them. So molecular compounds have to share their electrons. All right. Because they have to share them in order to be happy, they are far stronger when they are together than an ionic compound. Okay? They are what we call a covalent bond, which means they share an outer electron. Okay? So when we got an ionic compound, like we said, the electrons will switch. Okay? But when we're in a covalent bond, they are shared. So look in here, this is water. Okay, and water is a molecular compound, believe it or not, even though hydrogen is kind of a metal. Okay, this is a molecular compound, and okay, we're looking at the electron from hydrogen is right here. This is an electron from oxygen. Now, because of the fact that they have to share, this electron spends a lot more time in this area than it does out over here. Right? What actually happens is the orbit of this electron, okay, instead of being kind of a nice circle around the proton, it becomes more like this. Okay, and it actually orbits kind of both, and it spends more time near oxygen. Okay, meaning it's shared, but it's not shared perfectly equal. Okay, so it's shared a little bit. Right? So because they have to share each other's electrons, they can't leave each other either. Right? That makes these far stronger bonds, which is why most of the time molecular compounds are not as soluble in water as their ionic counterparts. Okay? Examples, things that are molecular compounds would be things like butter. Okay? Does butter dissolve in water? No, nothing oily dissolves in water, right? Okay? And oils are molecular compounds, right? They just don't dissolve. Candle wax is a molecular compound. You put a candle in water, it doesn't dissolve. Okay? Things like that. So molecular compounds typically are less soluble because they're not going to split up into these separate parts. Okay? If they do dissolve, their solutions won't conduct electricity because when they break apart, they take their electrons with them and they all stay neutral. All right, so the things to remember here, obviously, okay, molecular compounds are two nonmetals, okay, and they have to keep their electrons, okay, so the electrons are shared, okay, between the two elements. All right, that's kind of the big thing there, the big differences. Now, since they're sharing electrons and there's no balancing of charges, are there more combinations possible for two elements to go together then? Okay. When we're talking about ionic compounds, we said when calcium and bromine go together, there's only one way they can go together. Okay? But if you're not worried about balancing your charges, is there more than one way two elements can go together? Yeah, and that's why we have to put the prefixes in for molecular compounds. Okay? We have to use prefixes because we don't know when these two things go together how many of each there would be unless we tell people. All right, so you need to know your prefixes from 1 to 10 at least. Okay, I kind of try on purpose to never make it more than 10. All right, prefix for 1 is mono. Okay, prefix for 2 is di. Prefix for 3 is tri. Prefix for 4 is tetra. Prefix for 5, penta. Okay, for 6, it's hexa. Okay, for 7, it's hepta. Okay, some people will also say septa, but if you say that in front of Mr. Real, who teaches Chem 20, he'll flip out. He hates that. I don't know why. Okay, so go with this one. Okay, number 8, okay, is octa. Number 9 is nona. So just like your shapes. Okay, and number 10 is deca. Okay, you got 2 nonmetals in a compound and you got to name it. How do you decide which one to write first? Okay, the answer is you just write them in whatever order they were given. Okay, if you get this compound here, okay, you write carbon first and hydrogen second. Okay, and just like in ionic naming, you don't change the name of the first one. Right? So this would be carbon tetrahydride. Okay, now I didn't put a mono in front of carbon here because it's the first one. Okay, I only use mono on the second element. Okay, if it needs it. I don't know why that is. The chemists just have to be difficult. Okay, but you don't put mono ever on the first one. Okay, if I had this instead, okay, then I would have dicarbon octahydride. Okay, something like that. All right, everyone with me there? Is that making some sense? Okay, so just one little kind of exception rule there. You never use mono on the first thing. Okay, questions so far? All right, so when you're naming those molecular compounds, like we said, they arise when 2 or more nonmetals react to form a new substance. The electrons are going to be shared. Okay, the differences naming here is that we do have to use the prefixes here because we're not going to get the swap and drop happen. Okay, so here's good news. If you don't like the swap and drop, you don't have to use it for molecular compounds because the prefixes tell you what numbers to write, which makes it a lot easier, really. Okay, so the examples we've got here, okay, this would be carbon disulfide, okay. This one here is wrong. What's wrong with this one? Ken? Yep. Right, it's got to be monoxide, okay. There's no prefix in front of oxygen. There's only one here, okay. We said this has got to be monoxide or monooxide with a hyphen. Doesn't really matter which way you write it, okay. So, as in ionic compounds, the "ide" suffix is only added, okay, to the last element or last word, okay. More complex one, P4O10 tetraphosphorus decaoxide. Okay. Now, on your periodic table, okay, you will see, because it's in color, okay, some of the elements are highlighted on there. Okay. These are what we call the molecular elements. That's different from a molecular compound. Okay. Molecular elements bond with themselves to form a molecule. All right? For example, the air you're breathing right now, the main gas you're concerned with is oxygen, which is O2. Okay? Oxygen is one of the molecular elements. It bonds with itself to form a pair. Okay? Any ones that are highlighted in yellow do the same thing. Okay? So you've got nitrogen, okay, which is actually makes up a huge chunk of our atmosphere, okay, like 78% or something like that, okay, of our atmosphere is N2 gas. We breathe it in, breathe it out, it has no effect on us, unless you change altitude or depth very quickly, and then it bubbles out of your blood and you get the bends, and it's very painful, okay. Oxygen, O2, okay, we got fluorine, okay, comes as F2, Cl2, okay, Br2, I2, and At2, okay, are our kind of twins. Okay, those would be our molecular twins. Okay, the other two, sorry, hydrogen also is a twin. Now, hydrogen's weird. It is both a metal and it can act as a non-metal as well. Okay, just be aware hydrogen's weird that way. Okay, it goes both ways. Okay, for the blue one here, for phosphorus, phosphorus bonds with itself 4 times. Comes as a molecule of P4. Okay, and sulfur bonds with itself 8 times and comes as S8 when it's by itself. Okay, so all of those, they come as 2s, 4s, or 8s when they are alone. Okay, that doesn't mean they always come that way in a compound. They don't. Okay, but when they're by themselves, okay, they bond with themselves, so they're not lonesome. Okay, everybody with me there? All right, we're going to leave it at that for today. Okay, tomorrow's podcast was probably going to review a little bit of what we just did. That won't kill you. Okay, and then it'll start on some naming practice and whatever. Okay, there's no quiz tomorrow because I'm not here to give it. Okay, but there will be one on Tuesday, and it will be on naming. All right, so over the weekend, you'd best spend some time getting proficient at that, okay, so that you can get 100 on that one.